You know, there are people who study math just for math's sake, and they just really like the numbers, and they really like the variables, and they like working it out. But really, the strength of math is that it can be applied to just about every other subject. I mean, where would psychology and sociology and social studies be without the math and the stats behind it? Where would the sciences be without the math behind it? We even could say, where would English be? What would Shakespeare have been able to do if he didn't have the math of the iambic pentameter, right? So math shows up in, where would music be without math? Where would art be without dimension and perspective and being able to do ratios and proportions? So math applies to everything. We're going to focus directly on science for the next little bit. So you just need to know a couple math formulas you already know and what they mean in science. All right, so we're going to start with the idea of displacement. If you've taken any physics class, you've talked about displacement before. Displacement is defined as the difference between the starting position and the final position. So the difference between initial and final positions. And it's over a closed interval from A to B. And so the formula that we already know that works displacement out is f of b, which is the final position, minus f of a, which is the initial position. Okay, that's displacement. Your displacement can be 0, but that doesn't mean you didn't go anywhere. Right? How could you make that argument? How could somebody say my displacement is 0, but my step counter still shows, 12,000? Okay, so if you end up in the exact same place you started, you did a loop, your displacement is 0. But trust me, you've walked miles. Okay, if you run on a track, round and round and round and round, okay, your displacement is nothing. Okay, you end up at the same exact place you started, but you sure feel like you've gone somewhere, and you certainly have. So displacement can be 0, even though the distance traveled is not. Okay, all right, rate of change. The rate of change is an average. Sometimes it'll even specify the average rate of change. The formula for that is the displacement formula over the time interval. So f of b minus f of a over b minus a. Which of our favorite friendly mathematicians does that remind you of? That's Leibniz, yeah. Okay, and it's also slope. It's y2 minus y1 over x2 minus x1. In physics, we call that the rate of change, the average rate of change. Then you get to the instantaneous rate of change. The instantaneous rate of change is the same thing as the velocity. We talked about that yesterday. Velocity is speed plus direction. The math behind that is the first derivative, f prime of x. So you have to be careful about rates of change. You have to watch out, does it say average or not? Okay, be careful about the two, that you're using the right formula, because you are going to get different results. We've already talked about speed as well. Speed is the absolute value of the first derivative. It's velocity without direction. So it's always going to be positive no matter what. Then in physics, you've got the next derivative, which is acceleration. Acceleration is defined as the second derivative. That's the rate of change of the rate of change. It's like a double rate. Your speed is your regular rate of change. How fast your speed is changing is your acceleration. The rate of change of the rate of change. That would be the second derivative. Now, once we know about acceleration, then we can answer another question about speed. So this is sort of a sub-note to this. The phrase speeding up. It's tricky in English. It really is an unfortunate thing that we use the word speed to mean something, but we use the phrase speeding up to mean something different. Okay, if we were in a different language, we would have different words for that, but we're not. We're using English. So there is a difference between having speed and speeding up. Those are two different things. All right, so how do you know if something is speeding up? Okay, if something is speeding up, f prime of x and f double prime of x share the same sign. That means either they are both positive or they are both negative. A lot of people get the positive part. They look at just speed or velocity and they're like, oh, it's positive, therefore it must be speeding up. That's not true. You can have positive velocity but still be slowing down. Anytime you come to a stoplight, you're doing that. You have positive velocity, you are moving forward, but you are slowing down because you are decelerating. Okay, speeding up only happens, and you can have negative velocity and still be speeding up. Try jumping out of an airplane. Okay, you have negative velocity, but you are also speeding up. Why? What else is negative besides just your velocity if you jump out of an airplane? Your acceleration due to gravity, that's negative also. And those two negative forces combined to give you the feeling of speeding up, which is what we call it in English. Okay, I wish we had a different word because it is sometimes confusing between speed and speeding up. All right, and then we don't say speeding down. What do we say? Slowing down. Okay, so then the other one is slowing down. And that also compares the first and second derivatives, the velocity to the acceleration. F prime of x and f double prime of x have opposite signs. They're working against each other. And if they're working against each other, then you will slow down. So, use my person jumping out of an airplane. If you also have a parachute, the moment you open your parachute, the parachute is going to give you a different acceleration. It's going to give you positive acceleration due to the wind resistance that is formed by the parachute. Therefore, you're going to feel like you're slowing down because you have negative velocity, but you've got the positive acceleration of wind resistance working against it. So that gives you the feeling. Okay, it's the idea of those two things working against or together. All right, and the last one is the idea of something called a jerk. And that's not like an ex-boyfriend is a jerk. It's the kind of feeling that you have when you slam on the brakes or when you accelerate really quickly. Okay, if you've ridden like Supreme Scream, if you've ridden like the Incredible Coaster at Disneyland or whatever, when you take off really fast, okay, this is the third derivative. And so this is the feeling of the rate of change of the rate of change of the rate of change. So it is, if your acceleration is how fast your velocity is changing, then the jerk is how fast your acceleration is changing. And when your acceleration changes very quickly, you feel that feeling of jerk. When your acceleration changes positively, you feel pressed back into your seat. That's your feeling of jerk. When your velocity acceleration changes negatively, then you're gonna, go forward and hit your airbag or whatever. That's the feeling of jerk. That's the rate of change of the acceleration, which is already the rate of change of the velocity. When you are in motion, these derivatives have value. When you are still, some of these derivatives have zero value. Okay. How about, let me ask you this. If the acceleration has 0 value, does that mean you're not moving? Okay, if your acceleration has 0 value, does that mean you're not moving? What does it mean you're doing? You're coasting, right? At a constant speed. So you're feeling like you're gliding. You're not getting faster or slower. You're just staying constant. You still have motion. Okay, when's the only time you don't have motion? When what is 0? Which of those things? When the velocity is 0, then you don't have motion. That doesn't usually last very long. Okay, did you ever go on the swings when you were little, like out on the playground? Okay, then you're going back and forth, right? That one moment where you reach the top part of you as high as you could go, like for a moment, for an instant, did you ever feel like you were just suspended there in midair? Like, oh, I wish I could just, and then of course gravity pulls you back and you go the other way. But that's that moment of no velocity, of 0 motion. It doesn't last very long, it's instantaneous. Okay, swinging back and forth. Okay, all right, so let's get some notation down. Now, I've been using whose notation in all of this? No. I've been using all primes, right? That's Newton, okay? Leibniz's notation helps us sometimes understand things a little bit differently. So, with Leibniz, we introduced the idea of the time. So you might have velocity being expressed as df dt. That means the variable now that we're using is the time variable. Okay, and it brings time into it. So anything you've got dt on the bottom, you're now going to be using time as your changing variable as opposed to something else. So I like that Leibniz allows us to use different variables. Okay, that's the rate of change of f with respect to time. That's how we read that. Okay, this bottom part right here is read with respect to time, or whatever variable is the changing variable. The changes in the time cause the changes in the function that's being described. All right, so let's work on a physics example, and let's really pick it apart. Some of you know some shortcuts to physics examples, but they only work because calculus allows them to work that way. So let's talk about something, a projectile launched. Okay, we're shooting something, maybe it's the model rocket class down at the middle school or something. So a launched projectile follows the path h of t, so the height is dependent on the time, of 160 t minus 16 t squared. And we're talking about feet, and we're also talking about seconds here. So a couple questions you would ask from a physics point of view, and then calculus will help you answer those questions. Okay, question A, find the maximum height. Now some of you know that the maximum height is also called the vertex. And you may even remember that there's a little shortcut to memorizing the vertex of a parabola. Okay, it's the values of negative b over 2a, and that will always find it. But do you know why negative b over 2a always works? And it's because calculus makes it so. So let me show you how the calculus is going to support that. Okay, well, what's happening at the maximum height? In that instant that it's reaching the pinnacle of its projectile. Okay? Okay, it's hanging suspended there. I wish you could do those old like Bugs Bunny commercials or cartoons. Have you ever seen those where the coyote like runs off the end of the cliff and he just sort of hangs there for a minute and then zoom, gravity finally kicks in? All right, so that's the suspended moment, of the instantaneous moment lasting a really long time. So here, if you want to find its max height, you actually want to find where the velocity is going to be equal to 0. Okay, so finding the max height, aka set velocity, equal to 0, because that's what's happening from a physical standpoint. So we'll calculate the velocity, so v of t is the equation 160 minus 32t. If I set that equal to 0, t turns out to solve very nicely for me. T turns out to be 5, and that's seconds. But does that answer the question? No. The question is, find the maximum height. What did I just find? I find the time at which the maximum height happens, but I haven't found the maximum height yet. And so what do I have to do with my 5 seconds of time? Plug it back in. Plug it back into the height equation. So then go back to h of 5, 160 times 5, minus 16 times 5 squared. That works out to be 400, and that's going to be in feet. The units of your answer are worth just as many points as the answer themselves. Okay? I have even been known to give points to a blank answer that had a unit on it. Like the person could not solve, and they just were stuck, but they knew that it had to have miles on it, so they put miles. Units are worth points. Okay? If I'm going to deduct points for units not being there, then I can give points for units being there. Okay? So units are just as important. All right, part B. When it reaches a height of 256 feet, what is the speed? So there's actually an in-between question that you have to answer before you can go right to what is the speed. When it reaches a height of 256 feet, what do we have to answer first? What? The when. We have to answer the when. Before we can answer the what is the speed, we need to know when is it getting to the height of 256 feet. So we're going to take our height equation, which was h of t equals 160 t minus 16t squared. We're going to set it equal to 256, and we're going to work backwards. Now here's where some of you, your algebra failed you a little bit on the last test, or was it a quiz? Last quiz? You forgot that squared things have to be set equal to what number before you can solve? Okay, so we need to set this equal to 0 first. So we're going to have negative 16t squared plus 160t minus 256, and that'll be equal to 0. I don't like negative numbers, so I'm going to multiply everything by -1 so I don't have to deal with them. I do notice that this can be factored. The number 16 is in common, so I can take 16 out. So I factor the number 16 out, which works great because that's going to factor perfectly. And I get t minus 8, and I get t minus 2. And so t is 2 and 8 seconds. That's the when. Why are there two answers to when? Okay, because when does it reach the height of 256? Once on the way up and once on the way down. Now I need to answer what is the speed. And so the speed is going to be the absolute value of the velocity. So I'm going to find, I already know my velocity at 2, and I want to put the absolute value around that. And I want the velocity at 8, and I put the absolute value around that. So my velocity is 160 minus 32 times 2, and it's also 160 minus 32 times 8. This is going to give me the absolute value of 96, and it's going to give me the absolute value of negative 96. So both of them have an answer of 96, and the units on that are feet per second. Okay, because speed is always positive. All right, last question of this section. when it hits the ground, what is the velocity? All right, here's another when and what. So you got to answer the when before you can answer the what. The when is when it hits the ground. And so instead of setting this equal to 256, what am I setting it equal to? Okay, I'm setting the original equation equal to 0. I'll solve for those two. I'll tell you that turns out to be 0 and 10. And then you can find the velocity based on both of those times. So you'll want to know what's the velocity at 0, and you want to know when the velocity is at 10. All right, I get 2 answers because it's on the ground twice. It's on the ground at launch, and it's also on the ground at impact.